All right, let's dive right into this explainer on the monumental challenges and, frankly, the perilous journey of Mars exploration. I want you to imagine, just for a second, walking outside on a clear night and looking up at the sky. If you know exactly where to look, you could often spot that distinct rust-colored dot. You know the one. For decades, the red planet has totally captured our imagination. It stands as this ultimate frontier for robotic and eventually human exploration. But as we're going to see today, transforming that little glowing dot in the sky into a physical destination, well, it's an absolute engineering nightmare. Getting to Mars, landing on it in one piece, and actually surviving its violently harsh environment is basically a masterclass in overcoming extreme physiological and environmental hurdles.
To start things off, we really have to address the elephant in the room. It's something many in the space community ominously refer to as the Mars curse. You see, historically, roughly half of all missions sent to the red planet have ended in catastrophic failure. A 50% failure rate. Actually, think about what that means in the real world for a second. If a commercial airline, or say a bridge building company, had a 50% failure rate, that industry would be shut down overnight. No question. Yet, when we look back at the sheer number of multi-billion-dollar probes that either failed to launch, completely missed the planet, or violently crashed into its surface, it becomes glaringly obvious that Mars is historically unkind to our spacecraft. It really shows how incredibly audacious we are to just keep trying.
And this timeline brilliantly illustrates the razor-thin margins of error in interplanetary travel. Back in the 1960s, early Soviet missions like Mars 1M couldn't even make it out of Earth's orbit before failing. Decades later, with far more advanced technology in 1988, the Soviet Phobos 1 mission was lost completely. And why? Because of a single tiny software typo. That one little keystroke accidentally deactivated the spacecraft's attitude control thrusters, sending it tumbling aimlessly into the void. And then there's the famous one. In 1999, NASA's Mars Climate Orbiter literally burned up in the Martian atmosphere because of a mathematical conversion error between metric and imperial units. Yeah, one team used metric, the other used imperial. In space, a simple typo or a basic conversion mistake can doom a multi-million-dollar mission instantly. It's the ultimate reminder of why your math teachers always tells you to show your work and check your units.
Section 1. The Interplanetary Void. We can really think of a Mars mission as the ultimate cosmic obstacle course, and the very first major hurdle is simply getting there. It's not just a matter of pointing a rocket at a red dot in the sky and pressing launch. Unlike sending satellites into Earth orbit, which can theoretically happen on almost any given day, missions to Mars are dictated by strict orbital mechanics. So think of Earth and Mars like two runners on a circular track moving at completely different speeds. The inner runner, Earth, is much faster. Minimum energy launch windows, which are the only times the planets align perfectly to make the trip fuel efficient, only open up approximately every 780 days. To put that into perspective, that's roughly every 26 months. If a space agency misses this window by even a few days, they have to pack up and wait over 2 years for the next one. This makes synchronizing mission stages, coordinating international teams, and managing all the logistics a complete nightmare.
Once a spacecraft hits that precise launch window and is successfully on its way, it faces up to 9 months of travel through the harsh interplanetary void. And during this transit, we aren't just dealing with technical hurdles, we are actively fighting the fundamental limitations of the human body. The spacecraft, and obviously any future human crews, are constantly bombarded by deep space cosmic and solar radiation, with absolutely no planetary magnetic field to shield them. Furthermore, astronauts would be subjected to the debilitating physiological effects of prolonged microgravity. This essentially tricks the body into thinking it doesn't need its skeleton anymore, causing severe muscle atrophy and bone density loss. You also have to factor in the immense psychological strain and the growing communication delays as the spacecraft gets further and further from home. We literally have to hack the human experience just to survive the trip.
Section 2. Entry, Descent, and Landing, famously known as the 7 minutes of terror.
Let's see how all this builds into the most nail-biting part of any Mars mission. Mars presents this incredibly unique, agonizing physical challenge. It has an atmosphere thick enough to generate immense friction, meaning you absolutely need a heavy heat shield to survive entry. But that exact same atmosphere is too thin to slow a heavy spacecraft down entirely with just parachutes. So you need a flawless, highly complex sequence of events: extreme heat dissipation, the violent deployment of supersonic parachutes, and finally retro rockets or innovative technologies like a sky crane to gently lower the payload. But here is the real kicker.
Because of the severe signal delay between Earth and Mars, which can be up to 20 minutes, remote control from Earth is physically impossible. By the time NASA gets the very first radio signal that the spacecraft has hit the top of the Martian atmosphere, the vehicle has already been sitting dead or alive on the surface for over 10 minutes. This entire high-stakes sequence must be executed completely autonomously by the onboard computers.
But when that autonomous system works flawlessly, the payoff is absolutely astronomical. We achieve incredible scientific triumphs. Through this terrifying EDL process, we've managed to land incredibly sophisticated robotic geologists, like the Curiosity and Perseverance rovers. And these rovers aren't just out there taking pretty pictures. They have completely revolutionized our understanding of Mars. They've conclusively proven that liquid water once flowed across its surface, and they're actively searching for signs of ancient microbial life. More importantly, they're our vanguard. They're acting as robotic scouts, paving the way and testing the vital technologies we'll need for the eventual human element.
Section 3. Surviving the Red Planet.
So the crucial point is this. Once you conquer the launch, survive the radiation of deep space, and somehow successfully navigate those 7 minutes of terror, how do you actually survive an environment that is actively trying to destroy your equipment? Well, the Martian environment is brutal. Compared to our comfortable Earth with its thick, life-sustaining atmosphere, Mars has an atmosphere composed almost entirely of unbreathable carbon dioxide. The atmospheric pressure is a mere 1% of Earth's. For the human body, that is effectively a vacuum. Couple that with average surface temperatures hovering around -80 degrees Fahrenheit or -60 degrees Celsius, which, by the way, is colder than a brutal winter night in the heart of Antarctica, and you have an incredibly hostile world.
What's really fascinating here is the compounding nature of these threats. Because Mars lacks a protective global magnetic field, the surface is constantly irradiated by cosmic and solar radiation, posing massive, long-term risks for both sensitive electronics and human biology. On top of that, Mars is notorious for massive dust storms. Now, the Martian regolith isn't like beach sand. It's as fine as talcum powder. It carries a static charge, clinging to absolutely everything, getting into tiny mechanical gears and destroying air seals. In fact, these storms can grow to literally engulf the entire planet, as we saw with the Soviet Mars 2 and 3 missions and NASA's Mariner 9. These storms coat solar panels in that ultra-fine dust, suffocating a spacecraft's power supply. Add in the extreme scarcity of liquid water, and it becomes clear that any sustained presence requires miraculous, zero-fault engineering.
Section 4. The human element.
This brings us to the most delicate, complex, and frankly vulnerable payload of all in our future exploration plans: us. Humans. Sending robots is incredibly hard, sure, but keeping humans alive and sane on Mars is a challenge on an entirely different level. Imagine living in a confined RV with 3 of your coworkers for 2 straight years. You can't ever step outside to get fresh air without putting on a bulky spacesuit. Furthermore, you won't be able to easily call home or have real-time conversations with your family because a simple hello text takes up to 20 minutes just to reach Earth and another 20 minutes for a reply. This intense isolation and confinement can lead to profound depression, interpersonal conflict, and a severe drop in morale.
Beyond the mind, the body remains under constant attack, even after landing. The microgravity experienced during the months-long transit severely degrades the cardiovascular system, making the sudden return to a gravity environment, even Mars's partial gravity, pretty dangerous. Sustained space radiation dramatically increases the risk of cancer, neurological degradation, and organ damage. To survive these physiological and psychological threats, we can't just pack extra supplies. We will need completely closed-loop life support systems. What does that mean? It means recycling every single drop of moisture, literally purifying yesterday's sweat and urine to brew today's morning coffee. We'll also need incredibly advanced radiation shielding and mandatory, rigorous exercise and psychological countermeasures just to keep the crew functional.
Section 5. The future of Mars.
Now, despite this harrowing obstacle course, the 50% failure rates, the brutal transit, the 7 minutes of terror, and the hostile, freezing surface, our innate, undeniable drive to explore pushes us forward into a new, incredibly ambitious era. The coming decade is absolutely packed with history-making missions. In 2026, Japan plans to launch the MMX mission to study the Martian moons and actually bring a physical sample of Phobos back to Earth. Then, in the late 2020s and early 2030s, we are looking at the holy grail of robotic exploration, Mars sample return. China's Tianwen-3 mission, alongside a massive collaborative effort by NASA and the European Space Agency, aims to collect pristine Martian soil and launch it back to Earth. Just think about that for a second. We are literally transitioning science fiction into reality by attempting to build and autonomously launch a rocket from the surface of another planet for the very first time in human history.
But as we master this cosmic obstacle course and push closer and closer to a sustained human presence, we are left with a profound ethical question derived from these sources. Current planetary protection protocols exist to prevent Earth microbes from contaminating Mars. But what if we find indigenous Martian life, even just microbial life? If we discover that we are not actually alone in the solar system, do we still have the moral right to explore, exploit, and potentially colonize a pristine alien world? Well, that is a question we will definitely have to answer before we take our next giant leap. Thank you so much for diving into this explainer with me.